Morning, my dear students. I hope that you have watched the first video of the chapter Electric Resistance and Ohm's Law. In that we had discussed about the current density, relaxation time, mean free path. These three terms, relaxation time, drift velocity, mean free path, they are very important. Today we will start with Ohm's Law. So dear students, today we shall start with Ohm's Law. Ohm's Law gives out a relationship between the current and the potential difference. Okay. We all know that the current in the conductor starts to flow only when there is a potential difference that is applied across the end of the conductor. Okay. So George Simon Ohm gave a relationship between the potential difference and the current. He stated out that physical conditions remaining the same, the current flowing through the conductor is directly proportional to the potential difference applied across the end of the conductor. If the physical conditions remains unchanged, then the current flowing through the conductor is directly proportional to the potential difference applied across the end of the conductor. So we will see this Ohm's law. Here I is directly proportional to V. Okay. More the potential difference applied across the end of the conductor, more is the current. This is a very small example I am giving you. You get different types of cells. Some are pencil cell, some are bigger cell, and they are giving you different amount of current. Okay, the current value is different. Okay, so you have seen that small cells, pencil cells, they are used when the current required is very small, and if you require a heavy current, then you use batteries. Okay, so we are talking about Ohm's law. Ohm's law is I is directly proportional to V, or V upon I equal to constant. So V upon I is equal to 1. Now what is this constant known as? This constant is known as resistance. So resistance is the ratio of potential difference to the current. V upon I equal to R. If we draw a graph, of I versus V, then the slope of this line, we can see that the potential increases, current increases. Potential increases, current increases. So what are we getting here? With the increase in the potential difference, the value of the current also increases. Now the slope of this graph gives you the V upon I. That is I upon V is the slope of this graph will give you 1 upon R. That is the inverse of resistance. Okay, it is I versus V. It is I versus V. Therefore, its slope will be y-axis upon x-axis I upon V, that is equal to 1 upon R. This is slope. Slope is equal to 1 upon R. That is known as conductance. So V upon I equal to R, or I upon V equal to 1 upon R. Now we will discuss the experimental verification of Ohm's law. So we will see practically whether the Ohm's law is followed for metallic conductor or not. So what we will do, we will have a experimental setup in which we will be having a resistance, and we will be finding out the current flowing through the resistance and the potential difference across the resistance. So what we will do, we will make up a circuit diagram in which we will put the resistance and the ammeter and voltmeter in the circuit. So here is the circuit diagram that is drawn for the experimental verification of Ohm's law. This is a battery, source of EMF. Okay, and a resistance across which the potential difference is to be varied, and a meter A, it is used for measuring the current flowing in the circuit. Then we have a key to close or open the the circuit rheostat. Rheostat is a variable resistance. Rheostat in a circuit is used to vary the potential difference applied across the resistance. Okay. So what we will do? We will vary the potential difference applied across the R, and then we will measure the values of I. Okay. Is it clear? So what is to be done? With the help of the rheostat, we will have the potential difference applied across the resistance varied. For every value of V, we will find out the value of I in the ammeter, and then we will draw a graph and find out the resistance of the circuit. Or first of all, we have to find out the verification of Ohm's law. So we will see how the current varies with the potential. So we will draw a graphical representation for the values that are obtained by the variance of V and I. So it has been observed that the values that are obtained when the graph is drawn, we get the values V1, a graphical representation, we get a graph like this. Okay, the graph is like this. So this is the graph, value of V and I. V increases, I increases. Now what we will do? We will have two values selected here, V1 and V2. Here I1 and I2. So we will find out the slope of the graph. The slope of the graph will be I delta I upon delta V, and that is equal to 1 upon R. So R, this is slope. So R will be equal to 1 upon slope. That is equal to delta V upon delta I. What is delta V? V2 minus V1 upon I2 minus I1. Is it clear? For a metallic conductor, generally we get a straight. For a metallic conductor, we are getting a straight line. Okay. So this is theta. Theta is the angle of inclination. So we can also write the slope R in terms of theta. R can be equal to tan theta, which is equal to delta I upon delta V. Okay. Tan theta, that is equal to V upon I. Okay. Tan theta is equal to delta I upon delta V. Exceptions of Ohm's law. When we are talking about the Ohm's law, the graph that is obtained is generally a straight line. But if the Ohm's law is not followed, then the graph will be curved graph. In that case, we will not get a straight line, we will get a curvature of the graph. Now, there are certain situations where we will not get a straight line. What are those conditions? Is the physical conditions that we have stated out in Ohm's law, that physical conditions should remain constant. If the physical conditions do not remain constant, then the resistance or the slope will not remain constant. Like for example, change of nature due to flow of current. With the increase in temperature, if the current increases, then with the increase in temperature, if the current increases, then the resistance of the conductor changes, and the VI graph does not remain linear. So if the temperature is not constant, in that case the graph will not be a straight line, it will be a curved graph, and in that case we will not get a constant resistance, we will get a dynamic resistance. Second, no measurable current in the beginning. This is observed. This case is observed in water voltmeter, where the measurable current starts to flow after a certain voltage V0 is applied. That is, immediately as soon as we start the value of the voltage increase in potential difference from 0, immediately we do not get the current. Certain amount of voltage is required, then only the current starts to flow. That is V0. At a certain voltage only we get the current starting in the circuit. So the graph is linear, but the observation is against Ohm's law, because Ohm's law says that as soon as the potential difference is applied across the end of the conductor, the current should flow if the conditions are constant. If the conductor is a metallic conductor, it will strictly follow Ohm's law. So the graph will be a straight line. These conductors are known as ohmic conductors. So metal is an ohmic conductor. If the conductors are not obeying Ohm's law, then they are known as non-ohmic conductor, and their slopes are not straight line. They are generally curved. So we have a few examples of non-ohmic conductors such as PN junction, diode, triodes, thermistors and semiconductors. These are non-ohmic conductors. So PN junction diodes, triodes, semiconductors, thermistors, they are examples of non-ohmic conductors. Okay. So we will see the graph. For example, we have got this graph of a diode. This is a graph for a diode. You can see that it's not a straight line. It is a curved graph. So the resistance is also not constant. So we will find out the slope at any 2 points. So slope will be given by this upon this. That is QS upon PQ. And that will give you the dynamic resistance, that is variable resistance. So similarly here we have got a PN junction that does not follow the Ohm's law. The second point that it comes about is dynamic resistance. If there is a small change in the potential difference across the end of the conductor, then there is a small change in the electric current. And the ratio of delta V upon delta I is known as dynamic resistance. So what is dynamic resistance? Dynamic resistance is delta R. Delta R is equal to delta V upon delta I. If there is a small change in the potential difference applied across the end of the conductor and there is a small change in the current, then we have a small change in the resistance. That resistance is small resistance, that is known as dynamic resistance. So for that, we find out the slope between any 2 points of a non-ohmic conductor. Next we have the derivation of Ohm's law. So let us take L length of wire whose area of cross section is A, and we apply a potential difference V across the end of the wire. Then the electrons, free electrons in the wire experiences a force. Okay, so when we apply the potential difference across the end of the wire, what happens? There is an electric field set up, and as a result a force is experienced by the free electron and they start to move, which results in the current. So we have taken L length of wire, A is the area of cross section. The force experienced by the electron is given by F equal to ma. So acceleration is equal to force upon mass of an electron. Now force is equal to QE. So it is the electron that is experiencing the force. So instead of Q, we will write charge E. E is the electric field upon M. Then we have a radiation. Electric field is equal to V upon D. So here the D is the distance between the two and where the potential difference is applied. That is the length of the wire. So it is equal to E V upon ML. Okay. Then we had a relationship between the current and the drift velocity. The relationship was I is equal to NEAVD, where N is the number of electrons, E is the charge, A the cross section area, and VD is the drift velocity. So what we will do? We will find out the drift velocity. Drift velocity is equal to I upon NEA. Okay, so drift velocity is equal to I upon NEA, and we know that drift velocity is directly proportional to the A tau, where A is the acceleration that is there and tau is the relaxation time. So what we do? We put VD is equal to I upon NEA. This is equal to A tau, so A tau is equal to I upon NEA. Now instead of acceleration from equation number 1, we have A is equal to EV upon ml. In A tau we substitute the value of A. A की value क्या है? EV upon ml. So EV upon ml into into tau is equal to I upon NEA. Okay. Then we have to find out the relationship between V and I because that's the Ohm's law. So we leave V on one side and take everything on the other side. So we cross multiply. What do we get? V is equal to M NE square tau L upon A into I. V equal to M NE square tau L upon A I. Now you look here. We are going to prove the Ohm's law. V is directly proportional to I or I is directly proportional to E. Now we see here M is the mass of an electron which is a constant. Number of free electrons is also constant. Charge of an electron is another constant value, tau. If the temperature remains constant, then the relaxation time is also constant. For a given length of wire and area of cross section, means L and A both are constant. So what are we getting? We are getting all these values to be constant. All these values are constant. And mass is constant. And charge is constant. And number of free electrons are constant. E, the charge is constant. Tau, relaxation time, which is dependent upon the temperature, is also constant. Then for a given length of wire and area of cross section, so L and A both are constant. What do we get? We get here V is directly proportional to I, and this is Ohm's law. So we have derived Ohm's law. V is directly proportional to I. So what will we write? V is equal to Ri. What will we write? V is equal to Ri. तो यहाँ पर अगर इस रिलेशनशिप में हम रखेंगे V इक्वल टू Ri, तो R की वैल्यू क्या आएगी? ये सारी वैल्यू R के बराबर हो गई. ठीक है, R की वैल्यू क्या हो गई? R इज इक्वल टू M अपॉन N E स्क्वायर टाउ L अपॉन A. So what is R? रेजिस्टेंस है क्या एक्चुअली? रेजिस्टेंस इज इक्वल टू M N E square tau L upon A. Okay, so this is the value of resistance. The next topic is specific resistance or electrical resistivity. When current flows in the conductor, the ratio of the intensity of the electric field at any point within the conductor and the current density J at that point is called specific resistance or electrical resistivity of the conductor. So specific resistivity is the electric field at any point to the current density at that point. Okay, what is specific resistance? Resistivity, the ratio of the intensity of the electric field at any point within the conductor and the current density J at that point is known as specific resistance or electrical resistivity. So we have a relationship rho which represents specific resistivity. Rho is equal to EJ. Rho is equal to EJ, where E is the electric field intensity and J is the current density. So we know that electric field intensity is a vector quantity and J, the current density, is also a vector quantity. We write the relationship in this form: E is equal to rho J. Okay, so we have a relationship: electric field intensity is equal to specific resistance or resistivity into current density. Now let us take a length of wire or let us take a conducting wire of length L, area of cross section A. We apply a potential difference V across the end of the conductor. What will happen? A steady current I will start to flow across the end of the conductor. Suppose the intensity of the electric field E and the current density J is constant at all points within the wire. So electric field is constant at all the points and current density is also constant at all the points electric field at any point within the wire is given by E is equal to V upon L. So if we are applying a potential difference V across the end of the conductor or a wire of length L, then the electric field is equal to V upon L and the current density J is equal to I upon A. Okay. Now we substitute the values of E and J in the ratio. Rho is equal to E upon J. So E upon J, V upon L, I upon A. We write here rho is equal to V upon I equal to A upon L. Now V upon I, we know from Ohms law, V upon I is the ratio of the potential difference to the current is resistance. So it is resistance and A upon L. So we get a relationship between the specific resistance and resistance. Specific resistance is equal to R into A upon L. So specific resistance is equal to resistance into A upon L. This equation applies to homogeneous isotropic conductor of uniform cross-sectional area subject to a uniform electric field. What is important? The area of the wire should be constant and the electric field applied across the end of the conductor should be constant. Now we will find out the unit of specific resistance. Unit of specific resistance rho. Now rho is equal to R. R की unit क्या होगी ओम? एरिया की क्या होगी मीटर स्क्वायर और लेंथ की क्या होगी मीटर. तो मीटर से मीटर कट गया. रो की यूनिट क्या आ गई? ओम मीटर. ओम मीटर. Okay. So the specific resistance unit is ohm meter. In this formula, if we put L equal to 1 and A equal to 1 meter square, then if here we put L equal to 1 and A equal to 1, then rho will be equal to R. That is, specific resistance will become equal to the resistance of the wire. So if we take a wire of length 1 meter and area cross section 1 meter square, then the specific resistance will be equal to the resistance of the wire. Is it clear? So it is the unit is expressed in ohm meter. So unit is ohm meter and the dimension for resistivity rho is NL cube e raised to power minus 3 a raised to power minus 2. This is the dimension for specific resistance or resistivity.